Welcome to the fourth and the last video of the compressible flow chapter. In this one, we're going to study different operating regimes of converging and converging diverging ducts. One of the most important concepts of this video will be chalked flow. Let's start by considering a converging nozzle operating in between two reservoirs as shown in the figure. Actual shape of the nozzle is not important at this point, other than that it's a converging one. The reservoir on the left is the stagnation reservoir. The one on the right is used to establish a certain back pressure, shown with PB. This can be achieved by using a vacuum pump which sucks out the gas from the right reservoir so that we have the desired back pressure there. Then we open a valve in the system to establish a flow through the nozzle. You can think of this system as an experimental setup that we use to study different operating regimes of a converging duct. One important detail here is the possibility of having the exit pressure, which is the pressure at the exit plane of the nozzle, to be different than the back pressure. As we know, in an incompressible flow, if a fluid jet exits from a chamber to its surrounding, the exit pressure is taken to be the same as the surrounding pressure, which can be the local atmospheric pressure. But for compressible flows, this is not necessarily the case. The exit pressure and the back pressure can be different. In our experiment, we will start by setting the back pressure to be the same as the stagnation pressure. When the pressures of the two reservoirs are equal, there won't be any flow through the nozzle. Then we will operate the vacuum pump to gradually decrease the back pressure and study the variation of pressure inside the duct. What we're going to observe is shown in this pressure variation plot. There are four distinct cases shown with numbers from 1 to 4. Case 1 is the no-flow case, when PB is equal to P0. Pressure is the same everywhere in the duct and velocity is 0. If we decrease the back pressure, a certain flow rate will be established depending on the value of the back pressure. Pressure will decrease smoothly between P0 and PB, seen here as case 2. Flow rate will increase as we keep lowering the back pressure. We can keep decreasing the back pressure until it becomes equal to the critical pressure P star, shown as case 3. At this point, the exit Mach number becomes unity, and the flow is said to be chalked. The flow rate we have at this point is the largest that can be achieved in this setup. We cannot increase the flow rate any further unless we change the stagnation properties. If we decrease the back pressure below the critical pressure, the properties inside the nozzle and the flow rate would not change. The pressure variation inside the nozzle for cases 3 and 4 are identical. The exit pressure would still be the critical pressure and the exit Mach number would still be 1. We cannot have pressures lower than the critical pressure inside the nozzle of this setup, and the Mach number in the nozzle cannot exceed 1. The difference between cases 3 and 4 is seen after the nozzle exit. In case 4, the gas will exit the nozzle at the critical pressure and will suddenly find itself in an environment at a lower back pressure. The exiting jet, called a supercritical jet, will adjust itself to this environment by non-isentropic expansions and contractions, shown here as oscillating pressure line. Critical pressure P star is a defining pressure value here. The nozzle is said to be operating at its critical state when the back pressure is equal to the critical pressure. Cases with back pressure higher than the critical pressure are called subcritical, and those with back pressure lower than the critical pressure are called supercritical. This slide provides a summary of the cases we discussed. The first thing to note is that this nozzle is being fed from a stagnation reservoir, and the flow in it always remains subsonic. There can be a supersonic flow in a general converging nozzle, but not in the one used in our experimental setup. Chalked flow is achieved when the back pressure is lowered down to the critical pressure. For chalked flow, exit Mach number becomes 1. If PB is lowered further, flow remains choked and the mass flow rate does not change. Critical pressure is the pressure when the Mach number is 1. We can use the equation shown at the bottom of the slide or the Appendix C3 table to find that for air, P star is equal to about half of the stagnation pressure. To be precise, the nozzle first becomes choked when the back pressure is lowered down to the critical pressure, which is 0.528 times the stagnation pressure. And this slide provides another summary of our converging nozzle experiment using two new plots. The one on the left shows how the exit pressure changes with the back pressure. For cases 1, 2, and 3, exit pressure and the back pressure are equal. But for case 4, which is the supercritical case, exit pressure is the critical pressure, which is higher than the back pressure. The plot on the right shows the variation of the mass flow rate with the back pressure. Case 1 is the no-flow case, with back pressure being equal to stagnation pressure. Mass flow rate is 0. As we lower the back pressure, mass flow rate increases. This continues up to the point where the maximum possible mass flow rate is achieved. At this point, the nozzle is choked. Lowering the back pressure further does not change the mass flow rate. These two exercises are about the operation of converging nozzles. Solution of the second one is available in the solved examples handout. Let's now repeat the experiment for a converging diverging nozzle. It again operates between two reservoirs. We start the experiment by setting the back pressure to be the same as the stagnation pressure of the upstream reservoir. This results in the no-flow case, shown as case 1. Lowering the back pressure creates a subsonic flow throughout the duct. Flow accelerates in the converging part, resulting in pressure decrease, followed by deceleration in the diverging part, resulting in pressure increase. This behavior is similar to that of an incompressible fluid. If we keep lowering the back pressure, we arrive at case 3, which is a special case because it corresponds to choked flow. Mach number at the throat is now 1. Flow accelerates in the converging part all the way to Mach number 1 at the throat, and the pressure at the throat becomes the critical pressure. Flow decelerates in the converging part, resulting in pressure rise. Flow is subsonic everywhere in the duct except the throat. Choked flow is special because it delivers the maximum possible mass flow rate for the given stagnation properties. As long as the stagnation properties are fixed, no matter what we do, we cannot increase the mass flow rate any further. If we lower the back pressure more, cases similar to case 4 are obtained. These cases have supersonic flow with a shock wave in the diverging part of the duct. Flow in the converging part is the same as that of case 3. It is choked with Mach number 1 at the throat. But after the throat, flow continues to accelerate and becomes supersonic. Pressure keeps decreasing in the diverging part, but this cannot continue all the way to the exit due to the specified back pressure. In order to exit with the specified back pressure, flow goes through a normal shock wave. Pressure increases suddenly and the flow becomes subsonic. The rest of the diverging part of the duct acts as a subsonic diffuser. Flow continues to decelerate, pressure increases, and the flow leaves the duct with the specified back pressure. Location of the shock and its strength depends on the back pressure value that we set. If the back pressure is just a bit lower than that of case 3, then the shock will occur just after the throat. It will not be a very strong shock, meaning that the property changes across it will not be that high. But if we lower the back pressure more, the shock will move towards the exit. It will occur at a much higher Mach number, and the property changes across it will be higher. It will be a stronger shock. The most extreme case of this is shown as case 5. This is the case where the back pressure is set to such a value that the shock occurs at the exit plane of the duct. This is the strongest shock we can have in this duct with the specified stagnation properties. This case is labeled as 5Y, meaning that the back pressure used for this case is the pressure after the shock located at the exit. The state before the shock, called state 5X, is as shown. Case 7 is a very special one, and it is called the design condition. If this duct is designed to accelerate the fluid in the stagnation reservoir to supersonic speeds, and most probably this is what it is designed for, then case 7 is the most effective way of doing this. Pressure variation is identical to that of case 5, but the back pressure is lower and there is no need to have a shock wave. Without any shock, this flow is isentropic everywhere. The remaining two cases are called overexpansion and underexpansion. For both cases, the flow inside the duct is the same as that of the design condition. The difference is after the exit. As you see, back pressures are different for these two cases. Underexpansion is obtained when the back pressure is set to a value lower than that of the design condition. As the name implies, with respect to the specified back pressure, the flow is not expanded enough inside the duct. In other words, its pressure did not drop enough. After exiting the nozzle, the fluid finds itself in an environment with a lower back pressure than it expects and tries to adjust itself to this condition through a series of non-isentropic contractions and expansions. To get overexpansion, the back pressure should be between that of cases 5Y and 7. And this time the flow is expanded too much for the specified back pressure. In other words, its pressure dropped too much or it accelerated too much. After exiting the nozzle, the fluid finds itself in an environment with a higher pressure than it expects. It is important to remember once again that after case 3, where the flow initially gets choked, all the further cases are all choked. They all have the same mass flow rate, which is the maximum that can be achieved by this duct with the given stagnation properties. In order to determine the full operation details of this duct, we need to determine the back pressures corresponding to cases 3, 5Y, and 7. These are the limiting pressures separating different flow regimes. Between cases 1 and 3, the flow is subsonic in the duct. Between cases 3 and 5Y, there is a shock wave in the diverging part of the duct. Case 7 is the important design condition. Overexpansion occurs between cases 5Y and 7, and finally underexpansion occurs below case 7. The next slide summarizes the different operating conditions of a converging diverging duct. We already discussed all these details. Here we have another summary with the help of two new plots. Mass flow rate versus back pressure plot is easier to follow. Between the no-flow case and case 3, mass flow rate increases by lowering the back pressure. But then, back pressure has no effect on the mass flow rate. Exit pressure versus back pressure plot looks a bit more complicated. Several cases, such as 1, 2, 3, 4, and 7, are on the diagonal line, meaning that their exit and back pressures are equal. This is not the case for cases 6 and 8. Compared to the back pressure of case 7, which is shown here as P design, back pressure of case 6 is higher, and that of case 8 is lower. Case 5 is special, and it has two pressure values at the exit, 5X and 5Y. It is because for this case there is a shock wave at the exit plane. At this point, I advise you to pause the video, go back to the beginning of slide 452 and watch the discussion about the converging diverging nozzle again. As always, you are also advised to read these details from your textbook. This slide shows the behavior of the exiting jet. For cases other than 6 and 8, the cross-sectional area of the exiting jet is the same as that of the exit plane of the nozzle. Case 6 is the overexpansion case. Back pressure is higher than the design pressure of case 7, and the exiting jet is expanded too much. The exiting jet is first squeezed by oblique shocks and then goes through a complicated process, details of which is shown in this figure. The jet goes through a series of compressions and expansions until it finds an equilibrium with the surrounding fluid. If you want to read the details of this process and study this figure in detail, its link is given in the previous slide. Case 8 is the underexpansion case. This time back pressure is lower than the design pressure. When the exit pressure of a nozzle is different than the back pressure, visually pleasing flow patterns known as shock diamonds and Mach disks occur. Here you see a takeoff photograph of the SR-71 Blackbird aircraft. Its engines are designed for high altitudes where it flies and where the surrounding pressure is low. But during takeoff, the atmospheric pressure is too high compared to the design condition, causing overexpansion. The non-isentropic expansions and contractions of the exiting jet create this beautiful-looking shock diamond pattern. Here is another photograph showing the shock diamonds seen during the takeoff of an F-16 aircraft. These patterns are also seen in rocket launches. You can see them in the launch of this toy bottle rocket. What we are looking at is the changes in pressure visualized using a high-speed Schlieren imaging system. Actually, this is a snapshot from a YouTube video, link of which is available in the description. Please have a look at it. The next two slides have two examples for the operation of converging diverging nozzles. You can find their solutions in the solved examples handout. This is actually the end of chapter 4 of ME 306. But if you look at your textbook, you will see that it has 3 more sections. If you find the subject of compressible flow interesting, you can have a look at those sections. They are not a part of our course, not because they are too advanced, but because we do not have time to cover them. The first one is constant area duct flow with frictional effects. This is known as the funnel flow. The second section that we're not going to study is about the effect of heat transfer in duct flows. This one is known as the Rayleigh flow. With friction and heat transfer, the flows of these two sections are no longer isentropic. And the final section is a very brief one about two-dimensional supersonic flows. These parts that we are not studying here are actually covered in the technical elective course ME 411. You may consider taking it next year. And this is the end of the compressible flow chapter. I hope you enjoyed it. The next one will be about turbo machines.